Okay, so today we are going to start the new chapter, which is chapter 6. The title of the chapter is the stability. It is the stability chapter 6. Chapter 6 we will going to start, and after that we have to look at two more chapters, 7 and 8. Okay, so hopefully very soon we are going to finish the uh, course, the syllabus. Okay, so stability. Let's start about the introduction. So today, what is the design objective when you are looking for a control system unit? Then you should design about you should have some objective like producing the desired transient response, reducing the steady state error, and achieving stability. So 3 points you should look at. One, the desired transient response. Two, reducing the steady state error. Three, achieving the stability. That is your goal. So you would like to achieve these three. That is your objective. Then say we already know that there are two kinds of response. One is forced response and another one is natural response. Summation of both is C. Okay. So for a bounded input, depend upon natural response, the system can be stable, unstable, or marginally stable. Okay. For a bounded input, depend upon natural response, the system can be stable, unstable, or marginally stable. A system is stable if every bounded input yields a bounded output. Okay. If input is bounded but the total response is not bounded, the system is unstable. Okay. See, that is the conditions actually. Okay. So let's look at some stability criteria. See, a system is stable if the natural response approaches zero as time approaches infinity. So this kind of system is stable. See, a system is stable if the natural response as the time increases, the response becomes zero. The response approaches zero as time approaches infinity. Okay, so that is a stable system. A system is marginally stable if the natural response neither decays nor grows but remains constant or oscillates. That is marginally stable. And the system is unstable if the natural response approaches infinity as time approaches infinity. Okay. Okay, let me draw it. The system, say, uh, that is a stable system. This system is stable. This is a stable system. Okay. And oscillating, that is marginally stable. This system is marginally stable. And finally, not actually like this. Let me erase this one. This kind of system is unstable. This kind of system is unstable. Okay. So this is stable, this is marginally stable, this is unstable. So three kind of systems are there. So three kinds of system are there. See, this is unstable system. This is margin stable. So definitions are there, and I have drawn the figure accordingly. Okay. Now, an important criteria we should look at it. Ruth criteria. Ruth-Harris criteria. By using this method, we can tell how many closed-loop system poles are in the left half plane, in the right half plane, and on this j omega axis. That means here S plane, the S plane, that is the j omega, that is sigma. So using this method, we can tell how many closed-loop system poles are in the left half plane. That means that is the left half plane. L left half plane, LHP. In the right half plane, that means this on the right half plane, and on the j omega axis. Okay. So using this method, we can tell how many poles are there. Okay. This system. First of all, we have to generate a data table, which is also called as root table. We have to generate a data table called a root table. Interpret the root table to tell how many closed loop system poles are in the left half plane, the right half plane, and on the j omega axis. So by interpreting the root table, we can tell how many closed loop poles are on the right half plane, on the left half plane, and on the j omega axis. Okay. So we have to do this. We have to generate a root table. That is important. We have to generate a root table to identify or to find out the poles. The poles. Okay. Uh, Now, some examples are there, like say overdammed system. That is overdammed system. That is underdamped system. That is undamped system. That is critically damped system. Okay. System called and the response according to the see the pole. And the overdamped systems are there. Pole on the left half plane. Okay. Pole on the left half plane. Just a minute. Hello. Hello, sir. ও আচ্ছা আচ্ছা হ্যাঁ হ্যাঁ মিঠু সাহেব জি জি বলেন হ্যাঁ জি আলহামদুলিল্লাহ ও আচ্ছা হ্যাঁ এটা আমি আজকে করবো আর কি হ্যাঁ, আজকে করবো। আর অ্যাকাউন্টে কি হয়েছে আচ্ছা আমি তাহলে এক্ষুনি মেল করে দিচ্ছি আপনাকে হ্যাঁ বিদ্যুৎ বিল 3 সার্টিফিকেট আর আমার ওই যে অফিস আইডির ইয়ে কপি হ্যাঁ হ্যাঁ ঠিক আছে হ্যাঁ হ্যাঁ আমি আচ্ছা আচ্ছা আমি এক্ষুনি দিয়ে দিচ্ছি Okay, sorry, I had to send a mail. Okay, for personal reason. Okay, so look at the table here. So here, if we have this kind of system, that means the overdamped system, then pole would be on the left half plane. And if we have the underdamped system, then pole position would be there. And if we have the undamped system, then pole on the j omega system, on the j omega axis. If we have the critically damped system, then pole would almost overlap. Okay, that is the thing. Now, so how to generate a basic root table? So that is the system, how to generate basic root table. Okay, so to generate a root table, so that is the basic equation. Let's look at this equation. Everyone, please be careful. So if you look at this equation, then from this transfer function, we have to generate a table. So look at the equation A0, A1, A2, A3, A4. These are the coefficient. These are the coefficient. Okay. So initially, you have to generate a root table. Say at the left half plane, at the leftmost column, mm, make uh, make a column of S. The power will start from the higher number, like say s to the power 4. Here the maximum power 4, fourth order. Okay, so it will be started from the s to the power 4 and end at the s to the power 0. So s to the power 4 to s to the power 4, s to the power 3, s to the power 2, s1, s0. Okay, that is the your leftmost table, leftmost column. Then from the first row, you start from the maximum power coefficient. You take the coefficient of the maximum power element, like say s4, s to the power 4, and the coefficient is a4. So a4. Skip the very next one. Skip the a3, then go to the next a2. A4, A2, A0, A4, A2, A0, then A3, A1, A3, A1, and here there is nothing, so it would be 0. So A3, A1, and 0. So that is your initial layout for root table. Okay, initial layout for root table. A4, A2, A0, A3, A1, and 0. Now you have to complete the root table. That is important. Just see this one. Here, first of all, uh, you have to generate a determinant, like say B1. How to generate it? Take the first column, A4, A3. Okay, last two row of the first column, the last two row, A3, A4 and A3, A4, A3. Then next one, A2, A1, divided by A3, immediate upper one. Similarly, and minus, it is the formula, it is for the minus from the formula. Similarly, A4, A3, A4, A3, A0, 0, A0, 0 divided by A3. And here, A4, A3, very next 0, 0 by A3. For the second one, for the C1, A3, B1, A3, B1, A3, B1, and A1, B2, A1, B2 divided by B1. For this thing, A3, B1, A3, B1, 0, 0 by B1. Okay. So in this pattern, you generate that table, you complete the root table. Okay. Now look at the example, then I think you will understand it more clearly. Make the root table for the system given below. they have given a system to to complete the root table. Okay, to complete the root table, they have made a system. So here, so you have to reduce it. So you have to reduce it first. At first, say here 1000, upper 1000, multiply it, say if you multiply it, then what would happen? Say s square plus 3s plus 2s, that means plus 5s, plus s square plus 3s, then 2s plus 6 plus 6, and again here is plus 5. Then again 1000 s cube plus 5s square 5s square plus 5s square 5s square plus 25s plus 6s plus 6s plus 30. So ultimately what would it become? 1000 s cube 10s square 10s square plus 31s plus 30. Okay, then you have to reduce this one. Okay, reduce this one. So what is the formula? Since it is minus, so here this one would be plus, okay. So ultimately if we add the 1000, then that would be 1030. So finally our transfer function would be like this, s cube plus 10s square plus 31s plus 31s plus 1030. Okay, so it would be rs, it would be cs. Okay, just add this upper one. Okay, with this one. Okay, now so after getting this one, we'll uh, write this one. So remember this one, 1000 s cube plus 10s square plus 31s plus 1030. Okay, now see, we take the coefficient first. So maximum power s cube. So we make a column s cube, s square, s1, s0. Now take the coefficient s cube 1, second, then 31, then skip 1, then here definitely 0. now 0. For the second one, take this 10, then 1, 1 0 3 0, this one, then here 0, 0. Okay, so we have made this one. Now we can reduce this one, divide it by 10, then you will get the 1 0 3 and 1 here. Now look at here, s to the power 1, this one, 1 1 1 1, 31 103, 31 103. So just do the calculation, 103 minus 31, it would be 72, minus 72. Here same, 1 1, okay guys, it would be 1 1 1 1 1 and 0 0, it is 0. Same thing happened here. Here 1 minus 72, 1 minus 72, 103 and 0, 103 and 0. So it becomes 103. Same thing, like this way we completed the root table. Okay, so like this way we can complete the root table. Now make the root table for the system given below. So according to the problem, so we have made the root table. But before making the root table, we should reduce the system. Reduce this system. Okay, reduce this system. Otherwise, it will be difficult for you. That is a closed loop system. Okay, that is a closed loop system. Okay, how to interpret the basic root table? So how to interpret here? Okay, that is important to know. Now that we know how to generate the root table, now we already know how to generate the root table. Let us see how to interpret it. So how to interpret it? The basic root table applies to system with poles in the left and right half planes. So basic root table applies to system with poles in the left and the right half planes. Systems with imaginary poles and the kind of root table that results will be discussed in the session. Simply stated, the root hierarchy requires that the number of roots of the polynomial that are in the right half plane is equal to the number of sign changes in the first column. So number of sign changes in the first column. Number of sign changes. So first column, how many times the sign changes? Twice, right? Plus 2 minus and minus 2 plus. So 2 times sign changes. So 2 pole on the left, on the right. Okay, so if the closed loop transfer function has all poles in the left half of the S plane, the system is stable. Thus, the system is stable if there are no sign changes in the first column. See this. The system would be stable. The system is stable if there is no sign changes on the first column. This table has 2 sign changes in the first column. 2 sign changes. The first change occurs from 1 to S square row to minus 72 to in the S1 row. The second occurs from minus 72 to S1 row, S0. Thus, the system figure is unstable since 2 poles exist in the right half planes. So, this system, the given system is unstable because 2 poles are on the right half plane. Okay. Now, look at the special cases. 0 only in the first column. What would happen if there is 0 on the first column? Determine the stability of the closed loop system. Example is given here. So you have to determine the stability of this system. 10 by s to the power 5 plus 2s to the power 4 plus 3s cube plus 6s square plus 5s plus 3. Okay. Now, let's make a root table. S5, let's take the first one, S5 to s to the power 0, S5 to s to the power 0, the leftmost column. Now, 1, 3, 5, 1, 3, 5, then 2, 6, 3, 2, 6, 3. Okay. Now here what would happen? Just see this one. Minus say 1 2 1 2 3 6 divided by 2. So this equation would be minus 6 minus 6 6 minus 6 divided by 2. So it would be 0 by 2. So it would be 0. Right. So this 0 comes here. Okay. Again for this one, let's see. Minus 1 2 here 5 3 divided by 2. So see this one 3 minus 3 minus 6. Right. 6. No, this is 3. Sorry, this is 5. 10 minus 10 minus 10 divided by 2. So it would be minus 7, but minus minus will be plus. So 7 by 2 for this one. Like this way. So when the 0 would come on the first column, then we have to replace the 0 by epsilon. We have to replace the 0 by epsilon, or yeah, just take the epsilon here. We have to replace the 0 by epsilon, then do the remaining works. Okay, then do the process as usual. Then you have to consider now make another table. What would happen if the epsilon would be positive? What would happen? Let's see. If the, let's say plus 1, if it is plus 1, then it would be minus 1 by, it would be minus 1. If it is plus, then minus 49. Here it would be positive. Okay, this one would be negative and this one would be positive. Okay, and what would happen if it is negative? Okay, sign changes. Now look at the sign changes. Here once and here once. That means twice. Sign changes twice. 2 times sign changes. 2, 2. So 2 times sign changes. So this system is unstable. There are 2 sign changes on S3 to S square row, S3 to S square and S square to S1. System is unstable, 2 poles in the right half plane. So 2 poles on the right half plane. That's why the system is unstable system. Why unstable? Because the sign changes on the first column. That is the special condition of the closed loop system when there is a 0 on the first column. Okay. Now what would happen if the entire row becomes 0? If your entire row becomes 0, then what would happen? Okay, that is another case, another special case. Okay, full row is 0. That is a special case. So here, determine the number of right half plane poles in the closed loop transfer function. So this is the transfer function is given. Okay, now see, as usual, you do this, and finally, let's see. On the S cube, you got the full row 0. If the full row becomes 0, then you cannot do the remaining jobs. Okay, remaining steps. That's why you have to make a tricks. What kind of tricks? Okay, let's see. Now, when all elements of the row become 0, then look at the previous row. Look at the previous one. Okay, look at the previous row. S to the power 4, right? So it is s to the power 4 plus 6s square, make a polynomial. Okay, creating polynomial from row above the zeros. See, creating polynomial from the row above the zeros. So create a polynomial here. Create a polynomial here. See, that is s to the power 4 plus 6 square plus 8. And then differentiate it with respect to s. Then 4s is 4s cube plus 12s plus 0. 4s cube plus 12s plus 0. Okay. All entries in the first column is positive. Now see. Now just put the coefficient here. 4, 12, 0. Then reduce it, divided by 4. Then 1, 3, 0. Then do the remainings. And after that, after this, look at the first column. All entries on the first column is positive, hence there are no right half plane poles. So there are no right half plane poles. All poles are on the left half plane. Okay, so the system is stable. Okay, now another important thing, interpretation of the table. Okay, now how to interpret this table? See, this is a S domain. The entire row of zeros will appear in the root table when a purely even or purely odd polynomial is a factor of the original polynomial. For example, s to the power 4 plus 5 square plus 7 is an even polynomial, right? That is even because 4 is even number. It has only even power of s, so it has the only even power of s, right? Even polynomials only have roots that are symmetrical about the origin. So it has the roots that are symmetrical about the origin. This symmetry can occur under three conditions of root position. The roots are symmetrical and real, the roots are symmetrical and imaginary, or the roots are quadrantal. Figure 6.5, this one, shows examples of these cases. Each case or combination of these cases, like 1, real and symmetrical about the origin. Real and symmetrical about the origin. B, imaginary and symmetrical about the origin. B, symmetrical but imaginary. C, quadrantal and symmetrical about the origin. Quadrantal, these are quadrantal, okay, but also symmetrical. Okay, in this even polynomial, it is this even polynomial that causes the row of zeros to appear. So for this even polynomial, the row of zeros appear. Thus, the row of zeros tells us of the existence of an even polynomial whose roots are symmetric about the origin. Some of these roots could be on the j omega axis. On the other hand, since j omega roots are symmetric about the origin, if we do not have a row of zeros, we cannot possibly have j omega roots. So if we do not have the zeros, row of zeros, then there would be no j omega roots. Is that the row previous to the row of zeros contains the even polynomial that is a factor of the original polynomial. Finally, everything from the row containing the even polynomial down to the end of the row table is test of only the even polynomial. Okay. Now look at the example which tells the everything. Okay, that is another example. Here, the row of zero appears at the s cube, row of zeros appears. So take the s to the power 4 plus 3s square plus 2. Okay, now do the remaining works. So finally, okay, how do we now interpret this root table? Now how to interpret this root table? In the first column, how many times root changes, sign changes? Twice, right? Plus 2 minus, minus 2 plus. 7 to 6, 6 to 5. Okay. So, and S4, and here all are positive. see, since all entries from the even polynomial at the s to the power 4 row down to s to the power 0 row are a test of the even polynomial c s to the power 4 to s to the power 0. Okay, these are the even polynomial. Okay, no sign change. We begin to draw some conclusion about the roots of the even polynomial. No sign changes exist from the s to the power 4 down to s to the 0 row. Thus, the even polynomial does not have the right half plane poles. Since there are no right half plane poles, no left half plane poles are present because of the requirement of the symmetry. Hence, the even polynomial must have all four of its poles on the j omega axis. These results are summarized in the first column. See, even polynomial j omega all are on the j omega, but before the even polynomial, before this, twice root the sign changes twice. So 2 on the right half plane and 2 on the left half plane. So 2 on the right half plane and 2 on the left half plane. Total 8. Because the maximum power is 8. So total number of poles are 8. See, that is the summary. Two sign changes, one from S7 row to S6 row and the other from S6 to S5 row. Thus, the other polynomial must have two roots in the right half plane. These results are usually other. The final tally is the sum of roots from each component. The even polynomial and the other polynomial as shown the total in the table 6.9. So that is the total number. That is the total number. See, it is unstable because of the right half plane poles. Since it has two right half plane poles, so this system is unstable. Similarly, another example they have given. You can check this one. How many times the sign changes? Twice. So this system is unstable. System is unstable, and it does not have the j omega pole because no rows of zeros are there. And another example 6.9, they use the k here. Okay, you have to reduce it. Okay, reduce it and do the job. Then put the values of k. Okay, so in this example, since k is assumed positive, if k is positive, then what happen? Or if k is less than 1386, then it would be negative. Then what happen? So all things they can consider. Okay, and if the k is 1386, what happen? Okay, so and then therefore the system is marginally stable. Okay, so that is our end of chapter 6. We have studied about the stability of the system. Stability. So you have to look at the problems here, given the problems here. So okay, I may give it to you in the final. Okay, so that is your overall the chapter 6. Okay, that is your chapter 6, and let me take the attendance.
Hello, sir. I have a question.
Yes, yes, tell me.
Sir, how can we reduce steady state error?
How you can reduce the steady state error?
Yes, sir.
Oh, that is another chapter. You can reduce the steady state error by changing some parameter. Okay, by changing the parameter of the system, like the input parameter or the inside parameter. Okay, like the feedback. Okay, or the actuator. That's another case. That's not related in this one. Okay, the hardware case.
Sir, it's related to hardware.
Yeah, it's related to hardware. Like there would be always a steady state error. Okay, not the 100%. Actually, it is not possible to make the 100% accurate. Just if you look at the lift. Okay, if you look at the lift, it is not all the time the align with the floor. Sometimes upper or sometimes lower. Okay, so this is 1810. 1810, 2020, and 27, 335. Okay, so let me check the attendance. Kaniko, what is your roll number?
17.
17. And 27 is also there. 19 is there. 37 is there. Okay, Saidul,
স্যার 13 স্যার
13. And
স্যার হ্যালো
hello, হ্যাঁ
স্যার ওই যে আব্দুল্লাহ স্যার একটু সমস্যা হচ্ছে স্যার ওইখানে স্যার কারেন্ট নাই স্যার আর মোবাইল চার্জ নাই সেজন্য স্যার বলতে বলছে আপনাকে
আচ্ছা সমস্যা নেই। And Abdi Hassan, roll number
33, sir.
33.
Yes, sir.
Okay, Abu Bakar,
Bolero, sir.
Abu Bakar,
15.
Abu Bakar, your roll number
15, sir. 15. 15.
115. Okay, and Abdi Hassan 17, right? And Murasi 23. Murasi,
Yes, sir.
roll number 23.
Yes, sir.
And Shoaib Gidi
28, sir.
28. Saidul,
স্যার
তুমি বলছো তোমার রোল কত?
স্যার আমার স্যার 13
আচ্ছা 13, হ্যাঁ। Okay, so how many students are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9 students are there. Okay, no problem. So I will upload this one inshallah today. So you check this one. Okay. Stability. Then tomorrow, that means the next class will start. That means the day after tomorrow, we'll start the chapter 7, which is the root steady state error. The chapter 7 is steady state error. In that case, you would see the steady state